Sagax Communications is a Hungarian SME, small medium enterprise, actually based on the software research, where we would like to utilize our experience and knowledge to implement cutting-edge radio frequency technology for different market segments, including defense and security, spectrum management, spectrum monitoring, space research, and space communications. Our main activity is hardware and software applied research, mainly system integrating and advisory consulting service for our customers. Our business strategy is based on making balance on research and development and engineering and consulting tasks. Our capabilities includes design and development of the state-of-the-art telecommunication and infocommunication equipments and systems. As an example, I would like to mention high-speed digital signal processing systems, microcontroller and programmable logic-based embedded design, configurable FPGA and programmable digital signal processing, and the internet connection-based control software and human-machine interface applications. This knowledge and technology base provide us the capabilities to offer technology for equipment and system-level integration. At our own site, we have engineering workstations and all the measurement and test capability for integrating the overall system and finish the finalized testing. Our high-end and high-tech products often add built-in signal processing solution to larger systems, such as wireless communication, radar beamforming, spectrum search and scanning, signal interpretation, electronic warfare, and testing and measurement system. As a result, we have high-quality products based on significant technological experience and many international users and references. In addition to the project, we strive to develop our own product range. It is significant to mention that during the design of our product range, we have taken steps in the development of universal and cost-effective building blocks, enabling us to develop projects on top of them, being competitive on the market and make competitive offers to our clients. Several types of different radio frequency direction finding methods already applied in the real life. All these different methods based on picking up the radio frequency signal and making additional calculations of the incoming samples or incoming streams of the signals. Radio direction finding is based on the measurement of the direction of the incoming radio signal and try to locate the source of this radio signal, which is practically a geolocation process. The method is used triangulation, which is based on the combination of different location of the radio direction finding equipment and measurement and individual results of this radio direction finding receiver. It is possible to run the geolocation process. This radio frequency receiver can use different types of antennas, including directional antennas, omnidirectional antennas, rotating or fixed antennas, and they are usually connected different radio channels and different types of radio receivers. We are working on development of our direction finding IP based on so-called full-wave interferometer, which is based on the multi-channel phase coherent radio platform. This is the latest modern technology to provide the fastest operation. The basic principle of the full-wave interferometer is based on collecting all the signals from all the antenna elements and radio channels in real time. In such case, provide the maximum amount of information we can utilize from the different antennas and different radio channels. We provide our IP for different radio receiver platforms, provide 4, 8 or 16 channels, which are the usual industry standards for such platforms. However, our IP can work arbitrary number of different antennas and radio channels. Processing algorithms can run general-purpose computers with high computing power, but even it is possible to transfer this IP running on an FPGA, which provides significantly higher computing capacity. The state-of-the-art multi-channel phase-coherent radio platforms usually provide built-in FPGA technology for down-converting the signal or slicing the part of the spectrum which is interested, and in this way it is possible to match the source and the computing power which is available in a given configuration. But we are ready to pour the whole IP into the FPGA for further increase the processing power and match the maximum instantaneous bandwidth of the radio receivers. This technology requires latest and state-of-the-art software-defined radio platforms, provide high channel count, high instantaneous bandwidth, and high precision of synchronization between the different channels of the radio platforms. Multiple levels of approaches are used for testing and validation for such systems. Of course, we use the available software testing methodology, which are usually available for different software development environments for our developers. Datasheet parameters such as accuracy and other performance indicators are validated using simulated RF signals and taking the advantage of the RF record and playback technology, where real signals recorded in the field can be used. In this test, we rely heavily on the NI LabVIEW programming language and NI technology in general. On the system level, we add real radio receivers to the DF test equipment, and we boot test it in laboratory environment and on the field. NI USRP is the most frequently used radio receiver front-end in our test, thanks to their easy of use, adequate support and mobility. For high-end prototyping and validation, we often utilize NI-PXI platform with the use of the vector signal transceiver and other FPGA-based co-processing PXI modules. In a field test, we have accessed the shortwave antenna system near Budapest in Hungary, and on the other side we also have access open field test for mechanically rotating platform. The core of the software IP is the algorithm itself, which is responsible for calculating the angle of arrival of the incoming radio frequency wave. The significant place of the system is built around the software service that is responsible for providing the ecosystem, such as connecting different radio receivers or serving client applications. This headless standalone service is able to run a wide variety of computing systems. It is possible to transfer to the FPGA processing unit. We highly rely on NI-PXI platform and the FPGA coprocessing unit based on this platform for advanced computing capacity. We build and provide high-level software interfaces and client programs to show for our customers how to use our basic core processing IP. Any type of radio frequency platforms can be used to provide a signal to our core IP until they meet the basic requirements of the computing, including the number of channels, the bandwidth of the channels, and the level of the synchronization between the channels. We have a built-in driver for 4 channels receiver version of the NI USRPs, including the self-calibration, which is developed in-house. Wide variety of different antenna systems and antenna arrays can be used with our IP. We also have the experience to propose the best antenna system for different applications to our customers. If our users want to leverage the multi-channel synchronous record and playback capability, we are also able to attach large storage capacity RAID system to our core IP solution. Direction finding technology can be used to determine the location of the radio frequency sources. As you can imagine, this is mandatory to find the location of the emitters, provide the spectrum awareness and spectral dominance in the battlefield, or find the disturbing and interfering signals in a commercial application. All results are encouraging. Based on the core IP we already developed, we are able to detect down to 1 millisecond signal with accurate location and geolocation of the position of the transmitter. There is no need to rotate or switch the antenna system that allows continuous scanning or monitoring in wide frequency range. Broadband processing of the radio channels allows us to scan the spectrum with a speed up to 8 to 10 GHz per second. The measurement accuracy is influenced by several factors, but the T-degree accuracy is reachable even for a moving source with the radio self-calibration we developed. Currently for the validation we are using the 4-channel radio frequency platforms, but we are planning to move and use up to 8 or 16 channels and increase the processing instantaneous bandwidth to provide the higher capability systems. We are also working on additional developments on multi-channel synchronous phase coherent platforms, which is our main application and expertise domain. One of them is the multi-beam digital beamforming antenna system for mobile and satellite communication. This is the cross-domain interdisciplinary solution between the space and the defense domain. Digital beamforming is a process where we are going to maximize our antenna gain towards a given source or a given direction of the signal. With this technology, we can increase the signal-to-noise ratio for the wanted signals and with some additional processing steps, reduce the level of the unwanted signals. Based on the digital signal processing, we are able to synthesize different beams towards the different target locations. This technology can be used to track moving objects with the synthesized beams, which is actually the electronically synthesized antenna aperture.